In 2009, a team of researchers in a Colombian coal mine pulled something from the earth, and it made them stop cold. It was a vertebra, thicker than a human wrist. At first, they thought it was just another giant crocodile, until the math didn't add up. They weren't looking at a lizard, they were looking at a snake, longer than a full bowling lane, and heavy enough to collapse the floor beneath it. When they calculated its final dimensions, they didn't celebrate. They refused to believe it. Because according to every law of biology we know, a 2,500-pound snake isn't just rare, it's impossible. Here is how a glitch in Earth's climate created a monster that shouldn't have existed. Today's ultimate giant snake, the green Anaconda, is the undisputed heavyweight champion of the modern Amazon. It is so intimidating that it spawned an entire horror movie franchise. Tipping the scales at over 200 pounds, a massive modern anaconda packs enough constricting muscle to crush the life out of an armoured caiman. Yet if you dropped it into the steaming swamps of the Paleocene epoch, 60 million years ago, it wouldn't even register as an apex predator. Compared to the monster lurking in those prehistoric waters, a modern anaconda is a child's pull toy. Evolution went completely off the rails with Titanoboa cerrigonensis. Its true scale is written in its bones. Sifting through the mud and ash of the sweltering Cerrejón coal mine in Colombia, racing industrial mining equipment threatening to destroy the fossilized rainforest, paleontologists unearthed solid columns of bone thicker than a grown man's wrist. A vertebra from the largest modern snake rests easily in the palm of your hand, relatively light and fragile. Lay two fully grown adult giraffes end to end on the ground, and this prehistoric serpent would still slither past their noses. Stretching 42 feet, longer than any animal you will encounter in a modern zoo, Titanoboa was impossibly thick. Its body was wide enough to completely plug a standard doorway, scaled sides scraping against the frame. Inside that immense girth was 2,500 pounds of coiled muscle. This cold-blooded predator weighed exactly as much as a Volkswagen Beetle. But a 2,500-pound snake cannot slither up a prehistoric tree or chase down prey across the dense jungle floor. Even monsters are bound by physics. Titanoboa was simply too heavy to be a traditional land predator. Slithering across dry land for extended periods would make gravity its deadliest enemy. Its own colossal weight would cave in its ribs and crush its internal organs against the earth. Instead, evolution turned this liability into a terrifying advantage, transforming the creature into a scaled submarine. Titanoboa retreated into the sweltering blackwater rivers of the prehistoric rainforest. Suspended in the dark water, this one-ton leviathan didn't lumber or struggle. It glided through the depths, silent, a shadow with no shape, no sound, just waiting for the water to ripple. A reptile doesn't just randomly mutate to this size. Evolution needed a biological cheat code unlocked by a completely broken global climate. 60 million years ago, the Cerrejón region of Colombia wasn't just the world's first recorded neotropical rainforest, it was an atmospheric pressure cooker. Scientists cracked the secret of this environment by treating massive cold-blooded animals as paleothermometers. Calculating the sheer volume of this giant and the thermal energy required to keep its blood pumping revealed the Paleocene epoch as a suffocating sauna. Fueled by atmospheric carbon dioxide levels that would choke us today, the baseline temperature hovered between 86 and 93 degrees Fahrenheit. Not a summer high, a relentless year-round average. Cold-blooded animals are absolute slaves to their environment. They can't shiver to get warm or sweat to cool down. Their internal metabolism is a direct reflection of the ambient air. You might think metabolism is simply how fast an organism burns calories, but it's actually every single chemical process that keeps an animal alive: growth, digestion, circulation, movement. Every one of those processes runs faster in the heat. In today's cooler world, evolution places a hard physical cap on a snake's size before its biological engine stalls out. In the sweltering Paleocene greenhouse, that unyielding heat acted as a limitless, turbocharged external engine. It aggressively accelerated Titanoboa's internal chemical processes, converting ambient heat into faster growth, more efficient digestion, and raw, terrifying mass. Evolution simply bypassed normal-size constraints, inflating this predator to proportions that defy modern biology. But water changes this equation entirely. A 2,500-pound snake moving through a swamp still sounds like an exhausting, calorie-burning nightmare. And on land, you'd be completely right. Dragging that mass across mud and roots would be metabolically catastrophic, burning through energy reserves faster than any prey item could replace them. On land, Titanoboa's own size would have been its death sentence. In the water, the equation flips entirely. The river carried the full burden of Titanoboa's bulk, meaning its muscles no longer had to fight its own weight just to exist. Its internal organs weren't being compressed against the ground, which meant breathing was effortless and digestion ran efficiently. And critically, the Paleocene swamp water was heated by that relentless 90-degree atmosphere. It acted as a living thermal battery, keeping Titanoboa's metabolism firing at full power around the clock. The warmth of the water did the work that Titanoboa's body would otherwise have had to do itself. The result was a perfect metabolic loop. The river eliminated the energy cost of movement. The heat eliminated the energy cost of staying warm. And the combination freed up a staggering amount of biological resource to pour directly into one thing: size. Titanoboa didn't need to sprint to hunt. It didn't need to patrol territory. It sank beneath the surface, completely weightless, completely invisible, burning almost no calories at all, and simply waited for the water to ripple. It was, metabolically speaking, the most efficient apex predator the planet has ever produced. For millions of years, Titanoboa's reign was absolute. It was a muscular submarine that had perfectly conquered its environment. The fossil record reveals a brutal truth. Gigantism is a massive biological liability, and the bigger you are, the harder the planet can hit you. But Earth's climate is restless. Slowly, global temperatures began their long decline, and the atmospheric cheat code that built Titanoboa began to break down. The swamps cooled by a degree, then another. The rivers became more seasonal, the dense, humid world. The world that had carried Titanoboa's weight, that kept its muscles warm, that kept his rivers teeming with prey, that world was drying at the edges. Each degree of cooling made the next problem worse. When the temperature dropped, its digestion slowed first. A swallowed lungfish, a meal meant to fuel it for weeks, simply sat unprocessed in its gut, rotting instead of converting to energy. Its metabolism began to stall. Hunting trips that had once required nothing but weightless patience beneath the surface now demanded more effort from a body with less and less to give. The giant turtles vanished. The massive crocodiles vanished. The food web that had sustained a 1-ton predator quietly collapsed around it. No asteroid strike finished Titanoboa. No predator ran it down. The largest snake that ever lived didn't die fighting. It starved in slow motion until it simply stopped existing. It was defeated, not by a predator, not by catastrophe, but by a slight chill in the air. Its genetic legacy, however, never left. It climbed to the treetops. The modern boa constrictor, Titanoboa's direct descendant, waits in the jungle canopy, striking with lightning speed to catch bats mid-flight, winding its muscled coils around them and suffocating them in the dark. The monsters never left. Evolution just placed a permanent size limiter on them so they wouldn't starve to death in our modern, cooler world. The Amazon, you know, is not the real Amazon. It's a tame, cooled-down shadow of something far stranger. The anacondas you see on wildlife documentaries, the ones that seem impossibly large, are the miniaturized descendants of a world that no longer exists. Titanoboa is the proof. As paleontology shows us, climate doesn't just shape ecosystems. It actively defines the absolute upper and lower limits of what kind of life is even possible. For a brief, sweltering moment in Earth's history, the environmental conditions aligned perfectly to unlock a biological cheat code, allowing a creature that should never have existed to rule the suffocating swamps of ancient Colombia. It was built for a world that no longer exists. Too big, too heavy, too perfectly adapted to a heat the planet could not sustain. Titanoboa required an average year-round temperature of 90 degrees Fahrenheit just to maintain its massive size. Not a record-breaking heat wave, not an extreme summer, a sustained, relentless average. And that is the biological threshold at which evolution's size limiter switches off. The fossils buried in that rock aren't just history. They are a precise biological instruction manual. Heat the tropics to this temperature, sustain it long enough, and nature will build a 1-ton serpent again. And we are currently warming our planet at a rate the Earth hasn't seen in millions of years. The conditions that built Titanoboa are not ancient history. They are a temperature reading, and the world we are building has a name: Titanoboa.